Hi everybody, this is a lesson to allow me to go through some water potential problems with you. So first of all, make sure that you have paper out because these are new problems. I would suggest doing them right in your notebook. You are going to need a calculator. It's helpful to have the formula sheet, although I'm guessing that you probably have already memorized the formula and memorized the constants, but just in case you need it, it's good to have those things out. And again, these problems are very similar to the ones on the water potential practice problems 1 and 2, but I wanted to make sure I went through some with you. So the first question, what is the water potential of a cell with a solute potential of negative 7.5 kilopascals and a pressure potential of 6.4 kilopascals? So the first thing I want you to notice is that this value is negative. Solute potentials are always negative, whereas this one is a pressure being exerted pretty much by the vacuole pushing against the cell membrane, pushing against the cell wall. So because it's pressure being exerted, it's positive. You'll remember that water potential of pure water is 0, and any solutes added make it go lower. So that's why this is a negative number. So first of all, I apologize because I'm using this little writing thing and my writing's never good on here. So you want to remember that water potential is equal to the solute potential plus the pressure potential. So the solute potential is negative 7.5. You add the 6.4 to it, so you get 1.1 kilopascals, and it would be negative. And that would be our answer for this problem. All right, moving right along. If a cell's pressure potential is 4.6 bars, so I like to go ahead and write in the problem, label what they are. The solute potential is negative 8.5. What's the resulting water potential? So again, I'm doing the same thing. This is going to be equal to negative 8.5 plus 4.6. So that comes out to be negative 3.9. This time the unit is bars instead of kilopascals. All right, next problem I have. The cell from question 3 is placed in a beaker of sugar water with a solute potential of negative 4.0 bars. So this is the solute potential, and it's just in a beaker, not in a cell. So there's no pressure in a beaker. So here's my beaker. And here's the liquid inside of it, and this is negative 4.0. And I'm going to put the cell inside. So here's my cell, and the cell is negative 3.9. So negative 3.9 is higher than negative 4.0. My suggestion is to always put high and low above it. And so water is going to move out of the cell. Now I also have to make an arrow showing that there's also water going into the cell. This is almost isotonic. So at the very beginning, there's going to be more water going out of the cell than into the cell, but it's going to reach isotonic very, very quickly with these numbers. All right, next problem here. The value for water potential in root tissue is found to be negative 5.8 bars. So this is my overall water potential. And if you take the root tissue and place it in a 0.25 molar solution of sucrose in an open beaker, what's the water potential of the solution, and which direction will the net flow of water be? So what I'm going to have to do is figure out the water potential of the solution. So that's equal to negative ICRT. So negative I is 1.0, the ionization constant. C is the concentration, so that's 0.25. R is a constant, 0.0831. And T is the temperature. So if this is 20, you got to add 273 to have it be Kelvin. So that's 293. So I'm going to plug all that into my calculator, and I get negative 6.09. So again, this is the solution. So here's my container. In the solution, it's negative 6.09. And then I go back up to the question, and it tells me negative 5.8 is the root tissue. So here's the root tissue that was placed in there. That's negative 5.8. So this is higher, meaning it's closer to 0. This is lower, so there is going to be a net loss of water. But again, I'm going to draw a little arrow going this direction to show water's also going to move in. These are also pretty close, so it's going to reach isotonic very quickly. But in comparison, the root tissue right now is hypotonic, and this liquid has a lower water potential, so it's considered hypertonic. All right, next question. A plant cell with a solute potential of negative 3.2 bars. So I'm going to mark this is my solute potential. It keeps a constant volume when immersed in an open beaker solution that has a solute potential of negative 2.2 bars. So this is also YS. So what is the cell's pressure potential? So I've got to try and find this. So first of all, my open beaker solution, the water potential is equal to the solute potential. And if it is keeping a constant volume, that means that they're equal. So this for the beaker is going to be equal to this plus this, because this is for my cell. So this is negative 2.2. I'm going to fill in the values I have so far. The solute potential is negative 3.2. So I'm just solving for this, and this would have to be 1. 1.0 would be my value for the pressure potential. And I would put it in bars because all the other units are in bars. All right, next one. A plant cell with a turgor pressure equal to 6.5 bars, so that's my P, and a solute concentration, so this is my C, is placed in a beaker containing, okay, so that's C for the beaker, and the room temperature is 20 degrees, so I'm going to quick write plus 273. Calculate the water potential of both the cell and the solution. So what I like to do here for these problems is I go across like this, and I make a little T-chart. Again, I apologize for my handwriting with this thing. But I'm going to do the cell, and I'm going to do the solution. I like to do the solution first because it's really easy. It's always negative ICRT. There's no pressure on it. So negative 1.0. All right, the concentration in the beaker was 0.6. R is 0.0831. Temperature is 293. And I punch all this into the calculator, and I get negative 14.6. All right, then I go over here to the cell. And I always remember the cell is going to be this plus this. So first thing I want to do is solve the solute concentration. So again, I need to do the negative ICRT. So that's negative 1.0, go back up here, 0.24, 0.0831, and 293. I'm going to punch all that into my calculator, and I get negative 5.84. Now what I have to do is I have to say, all right, my water potential is going to be equal to negative 5.84, plus I need to add in the turgor pressure. So I go back up here, 6.5 was the turgor pressure. Oh, that's not going to work. It's going to give me a positive number. Well, I'll just do it all the same because it's really exerting a lot of pressure. So let me just punch this into the calculator. Minus 5.84. All right, I'm getting a positive value. So this is equal to positive 0.66. So this I am definitely going to mark high, and this I'm going to mark low, which means water always moves high to low concentration. So the water is going to leave the cell. That would be the direction of the water flow. And this actually does come out positive in this case because there's a great amount of pressure here. So that's why I'm getting this positive value. All right, on to the next one. This one I'm going to change up a little bit because this problem is exactly the same as it is in your example. So let me just change it a little bit. Let's change this and have it be 0.55. Let's change the temperature and say 25 degrees Celsius. And then the pressure, let's have that be 6.2. Okay, now we have a problem that's a little bit different than the one in your practice problems in terms of the number values, but it's the same type of problem. That's the goal, to go through all the same types of problems. So it says at 25 degrees, a cell with a pressure potential of 6.2 bars, so this I'm going to mark as my P, is in equilibrium with the surrounding 0.55 molar solution of sucrose in an open beaker. So this is C for in the beaker. What is the concentration? So they're asking me to solve for C of sucrose in the cell. So again, I'm going to set up my little T here, and I'm going to go cell and solution. All right. Again, I told you I like to do the solutions first because they're a little simpler. Negative ICRT. So I put negative 1.0. I changed that C to 0.55 and then 0.0831, and 25 plus 273 would be 298. And then I punch all this into my calculator, and I get negative 13.6. So that's the value for my solution. So over here on this side, this is equal to this plus this, and this whole thing is equal to negative 13.6. That is what this value is. So I know that because it said it was in equilibrium, so it made that part easy. So now I want to say negative 13.6 is going to be equal to my solute concentration plus, what did I change this to, 6.2? 6.2. So to get this alone, I go minus 6.2 on this side, minus 6.2 on this side, and so negative 19.8 is equal to this, the solute concentration inside the cell. So negative 19.8 is equal to negative ICRT. So that's equal to negative 1.0. Oops, 1.0. C, that's what I'm solving for. That's my X in this problem right now. R, 0.0831, and T, which is 298. So I'm going to multiply 1 times 0.0831 times 298. And I get negative 24.76. So that essentially cancels this out so that I just have C on this side, and I'll do this side divided by negative 24.76. A negative divided by a negative is going to give me a positive number. So positive, and I do the dividing, and I get 0.8. So 0.8 molar is equal to C. That's equal to the concentration of sugar inside of the cell if the cell and the solution are at equilibrium. That's how I chose to put 13.6 here, because I solved the solution's water potential and I got that to be negative 13.6. And of course I had to take that 6.2, which was the pressure, and add to it, and then I just solved for C. So I hope that this helped you. I'm going to load it so that you can go back and watch it if you need help. You have 2 practice sheets of problems like this, and the problems on the quiz and the AP exam and everything else are very similar to these. So make sure that you become very comfortable with them. If you have questions, mark them, star them. I will go over it again with you. And you know what is another great suggestion? Make up your own problems. You make one, you solve it, you give it to your friend, they solve it, and you see if you get the same answers.